Okay, welcome to Adventures in Mathematics. I'm your instructor, Alan Carlisle. Today we're going to look at change of variables. Specifically, changing random variables that are continuous. When I use the term random variable, I will imply continuous versus discrete random variables. The schematic on the present slide illustrates a random number generator, which could be anything from a computer program, which many programs using a basic language possess. F of x is our PDF, which is short for probability density function, and x is our random variable. Now, when a random variable is generated, it can change. Specifically, we're going to look at placing a random variable within a new function, call it u of x, and we're going to be interested in the probability density function, which we will assign the value g of u. We need to get these functions delineated and straight in our mind. U of x is not a probability density function. It is a random variable created from our original random variable by placing it as a dependent variable into a function. Now, this new function u of x could again be a random number generator within a computer program, or it could be a natural stochastic process. We begin by letting w equal u of x. Okay, remember u of x is our change of variable function. We will solve that for x so that x equals y of u. Remember, u is our new or changed random variable. The probability density function of this new random variable u is given by the formula g of u equals f of y of u. Remember, y of u is equal to x. So all we're doing is substituting into the original function f of x multiplied times the absolute value of the derivative of y with respect to u. It's a very simple formula, and we're going to, in essence, derive it in the next slide or two. All right, even though this presentation is not a rigorous derivation of the formula, it does illustrate the mechanics behind what's going on. If you recall from probability density functions, quite impossible to find the actual probability of a single random variable, just a continuous random variable, that is. The best you can do is find the probability that a single random variable x lies between two other random variables or within a given section of x or interval. If dx is our interval, then the probability that x lies within that is given by the area under our curve f of x. So that f of x times the absolute value of d of x is our probability for finding x within d of x. If we set that equal to g of u times the absolute value of d of u, divide both sides by the absolute value of d of u, we arrive at our function, our probability density function rather, g of u, which is f of x times the absolute value of dx by du, and putting it into this form, we get our formula for the change of random variables. Okay, we're going to begin by using a uniform distribution. The reason for this is because many basic programs utilize as a basic command RAN1 or RND1 depending upon the program itself. You can download QBasic or BBasic, and I believe it's RND. I don't remember if it's RAN or RND for the Texas Instruments, but you can find that out in your command section of your Texas Instrument graphing and programmable calculator. But be that as it may, these commands generate random variables between 1 and 0, between 0 and 1, with a uniform distribution, which means that every random variable is just as likely to occur as another one. This is given graphically here. Between 0 and 1, f of x equals 1, and f of x equals 0 for all other variables outside of the domain of this probability density function. By the way, it's important to note that the area within this is equal to 1. Okay, if you want to increase your uniform distribution to include all random numbers between 0 and some other constant value, call it a, to keep the area under the f of x function, probability density function, equal to 1, and in this case it's going to be a rectangle, as you can see. The two adjacent sides have to be reciprocals of each other so that their product equals 1. This is illustrated in the generalized way of determining if you do have a probability density function by taking the integral from the lower limit of your random variables to the upper limit of your random variables of f of x dx must equal 1 in order for your function to be a probability density function. What we have here is graphically the graph of f of x having an area that you see colored here equal to 1, and in order to generate a random variable with a uniform distribution within the limits given here, you simply multiply a times the random variable presented in the previous slide, and on for example your TI programmable graphing calculator, you would multiply a times RND 1. That would simply give you a random variable with a uniform distribution between 0 and a. Okay, now let's begin by letting our change of variable function, u of x, be negative a times the natural log of x divided by a. We're not going to worry about where this came from. We're just going to simply say, let's generate a random variable having uniform density function 1 over a for some parameter a, and then we're going to place that random variable into u of x, the function u of x that we see here. Now what we are going to do to find the probability density function of u, our new random variable, is solve for x. Remember, that's the first step in finding g of u. And that's what we're doing here. The first step is to divide both sides of this equation by negative a, and we get this. Using the definition of natural log, we get x over a equal e to the negative u over a, and therefore x is equal to a times e to the negative u over a. Now, the next step, if you'll recall, is to take the absolute value of the derivative of x with respect to u, which gives us this result. And in the next step, we substitute into the formula for g of u. When we do, we get this very interesting, very important result, 1 over a times e to the negative 1 over a times u. This happens to be the all-important exponential distribution. And the reason why we get this, recalling that 1 over a is our original probability density function for x. Substituting this into the formula yields what you see here. Okay, it's interesting to note that this change of variable function u of x has a domain from 0 to infinity. U lies between 0 and infinity, as seen graphically here. Okay, now we're going to let our parameter a equal 2 for illustration purposes. You can check to see that 2 times e to the negative 2x does indeed fit the criteria of a probability density function by taking the integral from 0 to infinity of the function times dx and see that it does equal 1. In order to generate a random variable from a uniform distribution, again, we place our random variable into u of x given by negative 0.5. Notice that that is the reciprocal of 2 times the natural log of x over 0.5, and we will generate a random variable given the exponential distribution for any parameter we wish, remembering that this number will be the reciprocal of this parameter, and this number that I'm underlining here will also be the reciprocal of this parameter. Okay, this is a graphic illustration of the exponential distribution given the probability density function f of x equal a times e to the negative ax. By the way, the mean for this important distribution is 1 over a. As a increases, for example, if a equals 3, we have this, and as a gets smaller, a equal 2 begins to flatten out, and over time as a gets smaller and smaller towards 0, we see that it flattens out even more. The exponential distribution is quite often used to model the time between two random events, and is therefore very important, especially in such operations research topics like queuing theory, for example. Okay, let's take this analysis a step further. We can generate a random variable now in a computer program using a uniform distributed random variable and our change of variable formulas. We can generate a random variable with exponential distribution with any parameter that we choose, parameter a. Let's let this function f of x equal a times e to the negative ax be our new original probability density function. And what we're going to do, we're going to change this random variable with the function u of x equal the square root of x, and see what very interesting results that we get. Again, going through the process, we solve for x and get x equal u squared. Find the derivative of x with respect to u. Very simple. Derivative equal 2u. So that now the new probability density function for our change of random variable u becomes g of u equal 2a times u times e to the negative au squared when we make our substitutions, and using the formula given in red below. This new probability density function, g of u, is very interesting. We're going to study it next. Okay, our new probability density function, 2a times x times e to the negative ax squared, is given graphically for different values of our parameter a. Let's look at this. For a equals 3, we have this, a high hump, highly skewed to the right as it approaches the asymptotic x-axis. As x decreases in value, the hump gets smaller or lower, and so on until we get a equals 0.5. See how the change begins. Very skewed to the right, very interesting looking probability density function. This probability density function does have a name and is illustrated differently in most books. The probability density function 2ax times e to the negative ax squared, it can be found that the mean, interestingly enough, equals the square root of pi over 2 times the square root of a, and it is called the Rayleigh distribution. When we let a, our parameter, take on the value that you see here, 1 over 2 delta squared, we get f of x equals x over delta squared times e to the negative x squared over 2 delta squared, which is the way all books show the Rayleigh distribution. Delta is the mode, which is also the maximum value, or at the maximum value, I should say. Delta representing the random variable where the probability density function has the maximum value. And that is today's lesson. You might want to look up Rayleigh distribution on Google to see how it's used and related to certain natural phenomenon. This has been enjoyable. I hope you've learned something new. And now you can generate random variables using computer programs, including your programmable calculators. And you can play around with this formula to see what different types of random variables you can generate, and therefore simulate certain processes that occur in nature.